Welcome to Expert Insight Discover3D Printing seminar here on stage AM for you in Hall 11. I'm very happy that we have the topic with a groundbreaking additive manufacturing and with really basic information here. With me is Viktoria Krömer. She is our expert on stage. She is consultant and independent expert at ACAM. What is ACAM? ACAM is the Aachen Center for Additive Manufacturing, and the starting point for the seminar begins right now, and it will continue later, and we will have it each day here at the exhibition. So if you want at home, are curious about what the second step is, then you have to come to Formnext here in Frankfurt and to have to attend. But the first step we will have together right now. One advice to the colleagues here in the hall, as this is a silent seminar, make sure you grab your headset over there so that you can follow every step of our presentation here. Yeah, Viktoria, now I would say the stage is yours, and we're very interested in the basics in additive manufacturing. And well, have your time with the audience.
Thank you very much, and a warm welcome from my side. I'm very happy to be here today. Welcome everybody sitting in front of the stage and everybody following online. It's a pleasure for me to be here at Formnext. Welcome to our Discover3D Printing seminar. We'll dig into the basics of additive manufacturing today, so please follow along for the next 75 minutes and discover with me what additive manufacturing has to hold for you. Who's standing up here? My name is Viktoria Krömer, like what was already said. I'm a research associate at the Laboratory for Machine Tools and Production Engineering of RWTH Aachen University, but I'm also a consultant at the ACAM, the Aachen Center for Additive Manufacturing. What is the ACAM? I'll just give you a short introduction, as I will be giving more information on the ACAM later on. But the ACAM offers services in consulting, engineering, and research and education, just focusing on additive manufacturing. On the right-hand side, you can see our perspective and focus. So we are the one-stop shop for additive manufacturing, and together with all the expertise from the research institutes in Aachen, we can cover the whole value chain of additive manufacturing. In the ACAM, there are more than 100 researchers involved, and we have approximately 40 industry projects in consulting, engineering, and research yearly. So what you can expect today is, first, I'll give you a short introduction on the ACAM, and then we'll dig more into additive manufacturing. We'll go into the details of additive manufacturing technologies. I'll give you an overview on different technologies. Then we'll go ahead and dig deeper into additive manufacturing application examples, go along and see how you can successfully adapt AM. And then, last but not least, we'll look into the future perspective of AM and end the seminar with a summary. So hopefully you'll learn a lot today. I'm always happy to answer any upcoming questions afterwards, so feel free to just approach me. And I hope you'll enjoy the next 75 minutes here together with me. So starting a bit with the history of the ACAM in Aachen, why do we have so much expertise in additive manufacturing? We have a quite long history of additive manufacturing. You can see, for example, the first patent for SLM was filed in Aachen in 1997, and the ACAM itself was founded in 2015. So you can say that we are one of the world's most vivid and multifaceted AM ecosystem, and that's what makes us, the whole research landscape, and Aachen especially, so unique for additive manufacturing. Just to give you a quick overview on how the RWTH Aachen campus works and how it looks like, why we are such a unique research landscape. So the RWTH Aachen University was founded in 1870. We have more than 260 institutes involved, and we are a university of excellence since 2007. And what we try to do, we try to combine research and industry, so we do applied research and push it into industry and collaboratively solve challenges of the industry together with the research expertise that we in Aachen have. So within the RWTH Aachen campus, there are more than 400 companies enrolled, working together with our research institutes on just very different topics. And part of that RWTH Aachen campus is our cluster landscape. So we have 16 different research clusters, each focusing on a unique topic. For example, we have a cluster for biomedical engineering, we have a cluster for production engineering, and an innovation factory. And like I said, the point of those clusters is to just bring together companies and bring together industry and research and solve problems that industry may have. So always try to look at challenges from both sides and involve research and industry. So here again, you can see the Aachen Center for Additive Manufacturing, and what we do is we navigate AM complexity. So we combine all this expertise that we have in Aachen together with our broad industrial consortium with many different member companies, and are able to provide leading-edge research in AM. On the right-hand side, you can see our research institutes, each focusing on different parts of the AM value chain. So we have a very broad expertise, may it be in metal AM, may it be in polymer AM, and pre-processing, post-processing. Each of our research institutes has different focuses so that we are able to provide expertise in all challenges along the AM value chain. So summing it up, you could say that the ACAM is your one-stop shop for additive manufacturing, may it be for research, for consulting, education, or engineering. So let's dig a bit deeper into additive manufacturing. Probably, I would assume that most of you at least are a bit familiar with AM since you're here at the Formnext today, but we'll start off pretty basic. I'd like to start off with a definition of additive manufacturing. So there are many different definitions on the market. I'd start with the one from ASTM, according to which additive manufacturing is defined as the process that produces components from 3D model data by joining material, usually layer by layer, as opposed to subtractive and formative manufacturing methods. According to the VDI 3405, it's a manufacturing process in which the workpiece is built up in successive layers or units. So pretty basic, the definition so far. And on the right-hand side, you can see a couple of AM principles in life. So just giving a short overview on what makes AM different from subtractive or formative manufacturing, as most of you probably know, but anyways. So if you look at subtractive manufacturing technologies, you have a geometry, you have a defined workpiece, and you generate a new workpiece by just removing part of material. For example, milling or turning work that way. And then if you look at formative manufacturing, you have a given volume that you just try and put into a different geometry, like molding or deep drawing, for example. And then we have additive manufacturing, which, like we just learned, builds a part by stacking volume elements, usually layer in layer. So let's take a look at the global interest on AM according to Google Trends. On the left-hand side, you can see what the global relative interest is according to Google Trends. And we differentiate it in additive manufacturing and in 3D printing. And the yellow graph is 3D printing, and the purple graph is additive manufacturing. And the reason why the results for 3D printing are so much bigger is that 3D printing is just the more common term. Additive manufacturing is the more research term, and 3D printing is just what everybody pretty much knows it by. But what you can tell for both 3D printing and AM, that there is an overall positive trend of relative interest in all online search engines. So we started looking from 2010, and we finished in 2021, and you can see that there is a steep increase of interest in AM. And especially since 2013, 2014, you can see that steep increase of interest. And one time, Barack Obama said that 3D printing has the potential to revolutionize almost the way we make almost everything. So the question is, what is true about that statement? So there's different opinions. Some people say AM has the potential to provide solutions for everything. Other people say that it's just a big hype. And probably the truth is somewhere in between. And I think you can also tell that when you look at the fair, that the AM market knows what its challenges are, and that they are working on providing solutions to solve those challenges collaboratively. But then again, AM definitely does have many high potential that can be seized. And that's also what I would like to show in this seminar today, that additive manufacturing has high potential and offers many chances if you are able or if you get enabled to seize those chances. So let's take a look at the positive, historic, and future development of the AM market. What you can tell on that graph on the left-hand side, that the market size has been constantly growing since the past decades. The Wohlers report stated that during the last 20 years, there was an annual average growth of about 20% of the AM market. And you can tell that pretty clearly on that side. We have different reports and graphs included, but all of them state that there has been a positive growth rate and also predict that there will continue to be a positive growth rate. And the reason that the forecasts are diverging is because the market is pretty volatile and uncertain. So some markets predict a better growth, others predict a smaller growth. But all in all of them predict that there's going to be an increasing growth of the AM market. And included revenue here for those graphs or from the primary market for AM systems, software, material, and services. So let's take a look into which industries use AM already. AM is no longer just a niche technology like it was 30 years ago or something, and it's no longer just used for prototypes. So if you look at the different industries that AM is used in, and that's a survey from the Wohlers report, and they considered revenues generated from AM service providers, system suppliers, and third-party material suppliers. You can tell that there's a very spread use of the technology in many different industries, and a high share have the automotive or the aerospace industry with about 15%, but AM is also used in academia and medical and dental, for consumer products and electronics, power and energy, for military reasons, architecture, and many other industries that aren't included because they have a lower share. But for example, in the marine industry, AM is also being used, and it continues to be used even more. So now that we kind of know which industries AM is used in, let's take a look at the general process chain. And that's something that a lot of people underestimate. Additive manufacturing is not just I print a button and I have a part that comes out of it, but it involves a pretty complex process chain that's divided in pre-processing, in the actual in-processing, in a post-processing, and in work that you have to do when you have the final component. And it always includes a physical and a digital dimension, since AM is a pretty digital technology. So if we look at the pre-processing, what needs to be done before you can actually print a part? You have to make sure that you prepare the material that you need. You have to make sure that you prepare your production facility and that you prepare your machine. And again, on the digital side, you have to make sure that you have all the data that you need in order to prepare that part, both CAD and CAM data. You have to prepare your build job. You have to make sure that you have your production planning going in order to be actually able to print that part. So after you've done all that pre-processing, you go into the in-processing, which is where the part is actually generated, so where the physical generation of geometry takes place. So just like we just learned, where the component is built, usually layer by layer. The digital side on the in-processing is rather low. It's just executing the machine code that's been generated before and monitoring of the printing process. And then comes one of the biggest pain points in additive manufacturing, the post-processing. Because the post-processing, according to the technology and use case and part requirements, can be very extensive. It includes, for example, the build job removal and the cleaning of the part, but it also includes the part finishing, which can consist of many different process steps according to the industry, the use case, and the part requirements. Some steps just include, for example, support removal, heat treatment, surface treatment, or quality assurance. And in the digital dimension, you try and gather as many data as possible for quality assurance. And then when the part is done, you have some other steps regarding the final components, such as assembly, if necessary, labeling, packaging, and shipping, and also evaluating the data you've generated for longer-term improvement. And it's very important to understand the AM process chain and also to take into consideration the entire process chain when you try and design a part. Because what happens a lot of times is that people have a great idea for a part and they start with the pre-processing, they print it, and then they're kind of lost because they didn't take into consideration that there needs to be done something to the part when it's done. So it's always important to incorporate this whole thinking of pre, in, and post-processing when you actually think of a part that you want to manufacture. So just as a quick summary of the last few pages, what are the key characteristics of additive manufacturing? Additive, obviously, so the material is, the geometry is built by adding material instead of removing or forming. It's a toolless process, so meaning that the part geometry is independent from any tool, so you have almost any freedom of design. You can produce very complex parts and are not limited to any expensive or time-consuming tool generation processes. Then it's digital, so it's a direct manufacturing process based on 3D models. And it's kind of complex. If you're new to AM, you realize that there is a lot you have to consider, and especially that you require specific expert knowledge regarding the entire process chain. So if you're a designer or engineers have been designing parts the same way for 40 years, it's going to be difficult for them to just switch to an additive mindset. So you have to take into consideration that additive manufacturing is kind of complex depending on the technologies you're using, and that you need to take measures accordingly to successfully use AM. So last but not least for that chapter, let's take a look into the benefits and barriers that AM offers. And again here, it's important to understand that additive manufacturing benefits and barriers are not generic. So they are very specific according to the technology you're using, according to your use case, and according to the process chain that comes with it. For example, if you want to produce a prototype, of course, you have different requirements compared with the series part that you print in very high volume. But what are general benefits? General benefits are you have a very high design freedom. So you're able to produce very complex features. You can produce lightweight components and monolithic features. You are very flexible regarding design iterations. So if you say you don't like the geometry, you just have to change your part data, and you can just print it over again. You don't need to produce any tool or spend a lot of time before you can have any engineering changes made. You can integrate functions. For example, if you want to have a cooling channel in a part, you can just change the design in a way so that you can integrate cooling channels, which is probably not possible if you just manufacture it conventionally. You can have small quantities and individualization for almost for free, or at least economic compared with conventional manufacturing. You have very short time and efficiency idea to product. You have a short supply chain. And you have more ways to be sustainable compared with manufacturing technologies that have been established for many centuries. But if we take a look at the barriers, we also see that additive manufacturing has not only benefits to offer, but also barriers you need to take into consideration. For example, the printing times are fairly long, depending on the technology. So if you have a large metal part, it might easily take 24 or 48 hours in order to just print that part without the post-processing. The printing times can be pretty long. You have almost no economies of scale. And depending on the part, on the technology, you might have low surface quality, which you need to take into consideration for further post-processing steps. It requires an additive mindset and skills that are adapted to AM. And also, what you need to take into consideration is that AM demands you to transfer different health and security measures than other technologies. For example, if you work with metal powders, you need to take into consideration how you can protect your employees. And the last point is that the quality assurance and certification can be rather complex depending on the industry that you want to use additive manufacturing in. So summing up what we've just learned, we've learned what additive manufacturing in general is. We've learned what the general process chain looks like, and we've learned what can be different benefits and barriers of AM. And to understand those benefits and barriers is very, very important to successfully use AM for your own purposes. So now I'd like to go a bit deeper into additive manufacturing technologies. And to those watching online, I might not be able to finish due to the time, but I'll just start and we'll see how far we get. So if we look into the established metal AM technologies, there are many different ways to categorize AM technologies, but we followed here the Formnext AM field guide and also the DIN and ISO terminology. So there's different ways to categorize AM technologies according to energy source, according to material deposition, or according to the raw material you're using. And according to this terminology, we have 5 big categories. We have the powder bed fusion, we have direct energy deposition, we have material extrusion, binder jetting, and material jetting. So how do those different categories differ? So on the left-hand side, we have a powder stock where energy is inserted in order to fuse powder to a component. So we have the laser powder bed fusion, where you use laser as an energy source. And we also have electron beam melting, where an electron beam is used as your energy source. And then in the middle block, we have the direct energy deposition, where we don't have a powder stock or anything, but the material is deposited with the energy source together. And then we have the material extrusion, where we have a filament that's being deposited. We have binder jetting, where we have powder that's bonded with the binding agent. And we have material jetting, where the material is cured with heat. I will go into more detail on some of those technologies in a minute. This slide was just intended to give you a general overview on metal AM technologies. And sometimes within the terminology, there are different terms for the same technology. So laser powder bed fusion, for example, sometimes is called selective laser melting. Some terminologies are trademarked from different companies, but this is the official names that are used in the norms. So if we look into the segmentation of established polymer AM technologies, we have 4 big categories. We have the powder bed fusion, we have material extrusion, we have material jetting, and we have photopolymerization of resins. And again, according to the metal part, on the left-hand side, we have the powder bed fusion, meaning that we have a powder stock that's being fused somehow. We have the multi-jet fusion, where the powder is fused with an agent and energy, and we have selective laser sintering, where the powder is just fused with the laser. And then on the middle part, we have material extrusion, where we have a filament or a granulate that's being melted and deposited and solidifies when it cools down. So we stack the building layer by layer, either through filament or pellets. And then we have material jetting, where material is cured with UV light. And on the right-hand side, we have processing of resins, either cured with laser or cured with the projector. So it's important to understand that according to each technology, we have different principles of inserting energy. We have different options to produce raw materials. So we have pellets, we have filament, we have powder, for example, resins. So we're not limited to one type of raw material. Each technology uses different kinds of raw material, and it's important to understand which technology uses which material stock. So I'll just start with going a bit deeper into the technologies, and probably the live stream will be cut off after the metal part. So like I said, we don't have enough time to go into detail of all the technologies, but I'll go a bit more into detail on the laser powder bed fusion, the laser metal deposition, the ELA process, and also binder jetting. So if we look at laser powder bed fusion on the right-hand side, you can see the process in action. So how does it work? You have, as input, you have the digital model, the digital data of the part, and you have metal powder. And then it works in the way that powder is deposited, just one layer of powder according to the thickness of one layer you want to have. And it's selectively melted by terms of a laser beam, like you can see on the right-hand side. And then the build plate is lowered exactly by one layer strength, and the whole process starts again. So that subsequently you build up your part layer by layer, and then in the end comes a bunch of post-processing. For example, you need to get rid of the powder that didn't get fused. You have to might have to finish the surface of the part. So like I said earlier, there might be multiple steps involved with the post-processing until your part actually gives you the required, the requirements that you wanted for it. Laser powder bed fusion requires support structures for overhangs, for heat convection, and also to stabilize the part within the powder. So you always have to make sure that you tie those parts physically to the build plate instead of just placing them free within the build chamber. One advantage of laser powder bed fusion is that it has a general suitability for welded materials. So you have a very high material choice. For example, you can use steels, you can use nickel-based alloys, you can use copper, titanium, aluminum, magnesium, doesn't really matter. You're not really limited in choice of material. Laser powder bed fusion is the technology that's mostly used in industrial applications, so it has a very high process maturity. For example, AM Power always publishes a report on the technology maturity of different AM technologies, and laser powder bed fusion is the technology with the highest technology maturity reached, so it's a very stable process. Downsides of the process are it's relatively slow compared with other technologies, and you always, like I said, need to make sure that you tie the parts to the build plate, so you can't nest parts three-dimensionally inside the build chamber, but you always can stack them only two-dimensionally. All right, let's go into laser metal deposition, which process you can see on the right-hand side. Differing from laser powder bed fusion, you don't have a powder bed that's being fused, but you also have metal powder as input material and a digital model. And the way it works is the powder is in an inert gas flow, and it just gets, it gets put onto the substrate, and then it's successively melted. So differing from the laser powder bed fusion, you don't have a powder bed, but you just apply the material with each layer that you are that you're generating. And laser metal deposition is mostly used for AM, for additive coating, or for repair. And like I said, the powder is transported by an inert gas flow, and the energy is mainly deposited in the substrate, not directly in the powder. And again, it has general suitability for weldable materials, such as steels, nickel alloys, or aluminum alloys. It's much faster than laser powder bed fusion, so you have a much higher deposition rate, which is one advantage, but you're limited in the geometry that you're able to process compared with laser powder bed fusion, for example. So let's take a look into ELA, which is extreme high-speed laser metal deposition. It's the same principle pretty much as LMD, but it works only, or at least that ELA process works only for rotationally symmetrical parts. It has higher process speed than LMD, and you can apply very homogeneous coatings on those rotationally symmetrical parts. Again, the powder is transported by an inert gas flow, and ELA is something that's starting to come up more when you look into coding applications within AM, so it's a technology with high potential that's expected to be used in industry more in the future. So now for the last part of the live stream, let's look at binder jetting. There it works, okay. So like laser powder bed fusion, you have a metal powder bed, so you have powder that's deposited layer by layer, and the digital model as input. And then the way it works is the build platform is lowered, powder is deposited, and then a binding agent is applied. So instead of putting laser or an electron beam on top, you fuse the part by applying a binding agent. Binder jetting has the advantage that you are able to process very complex geometries. You don't need any support structures for that technology. And you can nest the parts three-dimensionally within the build chamber, so you're able to place many more parts inside compared with laser powder bed fusion. Downsides of the process are that when you have the parts, they are in a green state and very fragile, so you have a very extensive post-processing that you need to perform in order for the parts to give them their original functionality. For example, the curing, depowdering, and sintering to make sure the parts are no longer fragile and that you can actually use them for the use case you intended to do them. So compared with LPBF, binder jetting has lower technology maturity and less materials qualified, but it has a potential of higher productivity compared with laser powder fusion. So thank you for everybody watching online, and have a nice rest of the fair.
Yeah, it's your applause. Thank you very much, Viktoria, for these insights and these learnings from you. While here will be a short break in the live stream until 2 p.m., the second part of Viktoria's presentation will continue in the hall here. And for all these guys over there which came late, as this is a silent seminar, make sure that you grab your headset over there and you can follow the second part of Viktoria's presentation. Yeah, the audience outside there in the YouTube stream, we will see each other again on time at 2 o'clock, and then we will get some expert insights how to reconfigure international supply chains. We will see us.